Okay, Assalamualaikum warahmatullahi wabarakatuh. So this is continuation on the DC motor drive using the rectifier circuit. Okay, so this is example from the notes. Okay, a separately excited DC motor has a constant torque load about 60 Newton meter. Okay, so this is a constant, meaning that it is a straight line. The motor is driven by the full wave converter, and for this case, it's actually a rectifier, which is connected to a 240 volt RMS AC supply. Okay, and the field constant of the motor is given, which is KIF is equal to 2.5, and the armature resistance is 2 ohm. So the question is calculate the triggering angle, which is the alpha, so that the trigger angle, which is the alpha from the rectifier circuit, okay, for the motor to operate at 200 rotation per minute. So actually this is the summarize of what you should do from this question. Okay, so what is the firing angle, which is alpha, so that the motor can be speed up to 200 RPM. Okay, and this is the equivalent model circuit of the DC motor. So as you can see, we have no LA because this is in a steady state operation, so there is no change of the speed and so on. So it is actually, the motor is running at 200 RPM constantly. Okay, so there is no change of current and so on. And the VA here is actually the voltage output from your rectifier circuit. Okay, and the EA, which is your back EMF, the voltage which is produced due to the rotation of the motor, which is can be calculated by using this equation. So KIF omega. And I would like to highlight that the speed units for this should be in radian second, okay, radian per second, not RPM. So what you need to do is to convert this RPM unit into radian per second. So the conversion can be simply done by using this formula. So the rotation per minute multiply with the full rotation, which is 2 pi over the 60 second. Okay, because we have rotation per minute. So meaning that you need to convert into radian per second. So this one, 20.94 radian per second. So, and then, so we have already calculated this, okay? And then you can use this value to obtain your back EMF. Okay, your back EMF is KIF omega. So you just multiply with the KIF is given 2.5. So 52.3 volt here. Then you can obtain finally your EA, and RA is also given too. Then from that, okay, you can calculate your EA, but currently the I is not given. Okay, you have RA and EA. Our objective is to find the VA here. What is the voltage output from the rectifier? But right now we don't have IA. So the information from IA can be obtained from this top load. Okay, so because this is actually meaning that the motor is right now is connected with a load that has a constant torque, which is 60 Newton meter, meaning that the motor torque must produce the same torque of the load. Okay, so meaning that the torque produced by the motor is also 60 Newton meter. Okay, and we know that the torque relationship between IA is like this. Okay, torque is equal to, this is torque motor, is equal to the KIF IA, and KIF is 2.5. Then from that we can obtain your IA is around 24 ampere, positive 24, meaning that the current is going from the supply to the motor. Okay, so meaning that it is actually absorbing the power from the circuit. Okay, and then so we have finally obtained the IA. Then we have complete value here. So 24 multiplied with 2 plus 52.3. So this is actually your back EMF. Then you will obtain your VAC 100.3 volts. Okay, 100.3 volt, and the circuit used is actually a full bridge converter. Okay, it's not a three-phase, it's just a single phase full wave. Okay, so meaning that the voltage output average for the full wave must be this one, 2 Vm over pi cos alpha. Okay, so why we are using this? Because we assume that the motor has, okay, we assume that the rectifier is operated under CCM. Okay, I would like to recall back again that for the full wave control rectifier, there are two conditions. Okay, whether your rectifier is under continuous conduction mode or discontinuous conduction mode. Okay, so this condition is actually depends on the size of the inductor. Okay, and usually for the DC motor, the size of the inductor is very large compared to the internal resistance of the armature circuit. So by using that assumption, so we assume that the rectifier is operating under CCM. Okay, and CCM, so your voltage output equation should be this one. And okay, and then the voltage input is given in the RMS. So what you need to do is to convert into the maximum value. Okay, so you need to multiply with square root of 2. And from that, you will obtain that your firing angle is 62.3. So by using this 62.3, your motor will actually rotate at 200 RPM. Okay, so I think that is for example 1.